Hello, class. We're going to do a couple more examples of the independent samples t-test to make sure that we're understanding everything going on with this very important test. All right, so problem number 2. Suppose we randomly select 10 subjects from the Brenau occupational therapy program. And we have them complete the test that you take when you complete the occupational therapy program to make sure that you understand everything that you learned throughout that entire program. Okay, this test is the NBCOT. So for one of these groups, we're going to give them a super awesome study guide. Okay, this is going to be our experimental condition, and they're going to get Dr. Harrison's super awesome study guide. And they're going to take the exam. And the exam score is going to be the dependent variable. And then we're going to randomly select 10 subjects and put them in our control group. And we're going to have them study for the exam in their traditional way, and then we'll see their scores on the test. So we do this experiment. We have 10 subjects in both conditions. And we find out that the mean of our study group condition is 667 with a variance of 8,887. And our mean for the control group is 601 with a variance of 8,712.22. So we've got these, and we want to see if there is a significant difference between these two. If in the population, if we were to talk about the population means, are they the same or are they different from one another? So let's talk a little bit about the logic of the independent samples t-test. All right, unlike for the one sample test, we don't know the true population mean, okay? So it's going to be hard for us to draw a sampling distribution to theorize what that sampling distribution is going to look like under the null hypothesis. But have no fear, there's a way around this. So suppose, if you would, that we know truth, okay? We 100% know truth. Mind you, when we conduct this study, we don't know truth, and that's why we conduct this study. But we see that the true sampling distribution under the experimental group is this, and the true experimental and the true population mean sampling distribution for the control group looks like this. Okay. We would never know what the means of these distributions are what the means of these distributions are in the population when we conduct the study. But if we subtract one of these sampling distributions from the other one, okay, if we do that and there's no difference in the population means of these two sampling distributions, we're going to get a sampling distribution that's centered around 1, okay, or centered around 0. This is the sampling distribution of the difference between two independent means. So if we were to do this in our study and we know truth, we see that the majority of the time we're going to get a value that's less than 0, okay? Because as it turns out, our control condition, okay, or control condition right here, is scores less high, scores worse than our experimental condition. So we're going to see a sampling distribution that looks like this if we knew truth. Okay, so our job is to see whether or not when we subtract these two means from one another, if it is vastly different from 0. And if it is, we reject the null hypothesis. If not, we retain the null hypothesis. So if we have the true population variance, we could draw a sampling distribution of the difference between two means, and it would look something like this. But unfortunately, we don't have that population variance. So we're going to have to estimate it. Okay, so that's all theory. Let's go into the nuts and bolts. Okay, is there a statistically significant difference between our two groups? All right, so let's do the 4 steps. We're going to start off and have our null hypothesis be the population mean for group 1 and the equals the population mean for group 2. Which group is 1, which group is 2, that's completely up to you, okay? We could call the experimental group, group 1, and our control group, group 2. That's fine. We could do vice versa. Either of those, we'd come to the same conclusions, okay? The alternative is just does not equal there. Okay, this is standard for a two-tailed test. So now let's talk about our decision criteria. Alpha is 0.05. We have a two-tailed test. Okay. The other thing that we want to mention is that this is an independent samples t-test. Okay, independent samples t-test. Our degrees of freedom, this is big N, or the total number of our subjects, -2. So I could write it big N in -1. I could write it as the number of subjects in group 1 plus the number of subjects in group 2, all -2. There's 10 subjects in both conditions, 20 subjects in total, -2. We get 18 degrees of freedom. We look up in our table for the t distribution, and we find that the critical t, or t critical, is equal to plus or minus 2.101. So if the t value that we calculate is greater than positive 2.101, we reject the null hypothesis. If it's less than negative 2.101, then we reject the null hypothesis as well. If it's somewhere in between negative 2.101 and positive 2.101, we retain the null hypothesis. All right, so let's do some math. Okay, what we need to find, what we want to find is the sampling or the standard error. We want to find the standard error of the sampling distribution of the difference between two independent means. Okay, there's a few steps that we need to do to solve this. The first thing that we're going to do is we need to calculate our pooled variance. Okay, that's step one. Then what we need to do is we need to calculate the variance of that sampling distribution, the sampling distribution of the difference between two independent means. Okay, and I might write this as S squared difference. In the notes here, I wrote, instead of difference sub y1 minus y2, that's just the difference between those two means. Okay, so then when we find the variance of the sampling distribution between two independent means, we can find S difference, okay, which is the standard deviation of the sampling distribution between two independent means, also known as its standard error. Okay, so these are the steps that we can go into. And in fact, if we really wanted to, we can combine these two steps and go straight from S, the variance pooled, to S difference. And I'll show you all that here in a second. Okay, what is the formula for pooled variance? There's two formulas. There's a long formula and there's a short formula. There's a shortcut if specific conditions are met. All right, so the long formula that will work 100% of the time is as follows. Okay, our pooled variance is equal to the degrees of freedom for the first condition over the degrees of freedom total, I'm just going to put tot, multiplied by the variance of the first condition, added to, in parentheses, the degrees of freedom of the second condition over the degrees of freedom total, multiplied by the variance of the second condition. All right, this will work 100% of the time. The degrees of freedom for each condition is the number of subjects that are in that condition minus 1. So in this case, the number of subjects in both conditions is 10. So 10 minus 1 would be 9 here, 9 here. Okay. So it's the number of subjects in that condition minus 1. Degrees of freedom total, we've already calculated that. That's all the subjects that there are in the study minus 2. All right, the total number of subjects that are in this comparison minus 2. All right, so this will work 100% of the time. If, however, there's the same number of subjects in both conditions, this formula becomes simplified. This formula becomes the variance of the first condition plus the variance of the second condition all over 2. Now this is a formula that's familiar to you. Oh, it's not n, it's 2. Okay, or maybe that was a 2 and when I was writing it, and my handwriting is just really bad. Okay, this is an average. We're just taking the average of the variances, nothing special here. All right, if there's the same number of subjects in both conditions, we just take the average of the 2 variances, and that is our pooled variance. All right, so I have the formula up here for a pooled variance. That's the long formula that I wrote out for you. It looks a little bit different, but I promise it's virtually, this is the exact same formula. Okay, the formula for the variance of our sampling distribution of the difference between 2 means, that's what this formula is right here. And I mentioned here that this formula right here is simplified when we have the same sample size for both of our groups. Okay, so let's go and work this magic right here. Okay, so we have the same number of subjects in both of these conditions. So I'm going to take these 2 values, add them together, divide it by 2, and I'm going to find a pooled variance of 8,850. To get the variance of the sampling distribution of the difference between 2 independent means, I'm going to take the pooled variance and I'm going to multiply it by 1 over n1 plus 1 over n2. Okay, it'll be easier for me to just go back here. So the formula here for the variance of the sampling distribution of 2 independent means is equal to this. 1, the pooled variance all over 1, well, the pooled variance multiplied by 1 over n1 plus 1 over n2. And if I want to find the standard deviation of this, I can easily just take the square root of this entire expression, and that's what goes in the denominator of the independent samples t-test. Okay, so I multiply the pooled variance by 1 over 10, which is the number of subjects in the first condition, plus 1 over 10, the number of subjects in the second condition. And this is going to give me 1,770. At this point in time, I want to convert this, instead of s squared of the difference between the 2 means, I want to just get s of the difference of the 2 means, the standard deviation of this difference distribution. All right, to do that, I'm going to take 1,770 and I'm going to take the square root of that, and that's going to give me 42.07. All right, so I find this, and then I'm going to go back to ye olde t-test. I'm going to take, I have decided to make the first condition, the experimental condition, and the second condition, the control condition. And that's perfectly fine to do. I could do it vice versa. I'd come to the same statistical conclusion. And I'm going to get the t-value of 1.569. And since this is less than our cutoff value, okay, it's within the range of negative 2.101. And we'll see that our t-value is smack dab in the middle here, between negative 2.101 and positive 2.101. So this means that we're going to retain the null hypothesis. Okay, but we're not done just completing step 3. We need to calculate what the effect size is. So Cohen's d is going to be the difference between the 2 means all over the standard deviation, the pooled standard deviation. That's the word that I was looking for. So we're going to take the pooled variance, which is 8,850, take the square root of that, and that's going to give us 94.07. When we do this, we find an effect size of 0.702, which is a fairly large effect size. The reason why we didn't find a significant difference has to be a lack of power. That's a pretty substantial effect size. We don't find a difference because we don't have enough power to detect an effect. Okay, how would we write this up? So we retain the null hypothesis that the population mean for NB-COT scores is not different than for individuals studying using my super awesome study guide. I give you the descriptive statistics here, compared to the population mean for individuals in the control condition. I give you the descriptive statistics, and then I give you my statistics statement. T with the degrees of freedom 18 is equal to 1.569. Since we rejected the null hypothesis, I know the p-value has to be greater than 0.05. And Cohen's d is 0.701. That means that there is 7/10 of a standard deviation unit different between our two conditions. Okay. One more example here. So Roediger and Karpicki, two famous cognitive psychologists. Roediger definitely. Roediger has had his hands in many, many important findings in cognitive psychology, particularly within memory. And Karpicki is an up-and-comer. He was in graduate school here in 2006. He's made quite a name for himself at Purdue University. They're interested in the cognitive benefits of testing memory. Okay. So what they're going to do is they're going to have two conditions. One condition, people are going to read a passage, and it's a study condition. So they study it for, let's say, 3 minutes. They study it again for 3 minutes. And in the other condition, they study for 3 minutes, and then they test themselves for 3 minutes. So the amount of time that people spend with the material is exactly the same. But in one condition, they test themselves. In the other condition, they just study for an additional period. Okay. So subjects came back to the lab 1 week later and answered 10 questions about the passage. There were 11 subjects in the study condition, and participants had a mean of 5.4 with a standard deviation of 1.2. In the study test condition, there were 11 subjects with a mean of 7.6, and they questions answered correctly with a standard deviation of 1.6. So we need to conduct the appropriate statistic to see if there is a statistical difference between these two conditions. All right, so let's go and do that. So let's state our hypotheses. So again, we're going to have mu of condition 1 is equal to mu of condition 2. And I could do it like this, but I could name this something else. All right, if I were doing this in class for you guys, this is a mu. I might call this the study condition. I would say that it's equal to the population mean of the study test condition. I can abbreviate these however I want to. All right, so those are my hypotheses. Let's go through our decision criteria. Alpha is 0.05. We have an independent samples t-test because it's a between subjects manipulation, and we're comparing two samples. We don't have the population variance. We have a two-tailed test here as well. The total number of subjects is 22. 22 minus 2 gives us 20, and we can look up the critical value here, the critical t, which is plus or minus 2.086. So that is going to be our critical value. Now let's go and do our math here. Okay, to calculate the pooled variance, I don't have the variance here. I have the standard deviations, but I can easily convert those to variances by squaring them. Since they're the same number of subjects in both conditions, I can just add these two up and divide it by 2. As if by magic, we see that the pooled variance ends up being 2. Okay. The variance of the sampling distribution of the difference between two independent means, I'm going to use that. It's a bit of a mouthful saying that. Okay, so 2 multiplied by 1 over 11 plus 1 over 11. Okay, and this is going to give me 0.364. Okay, and I want to make sure that I take the square root of that to get S difference. Okay. In my study test condition, I have a 7.6, and in my study condition, I have a 5.4. I take the square root of this for my S difference, 2.2 all over 0.604, and this gives me a t-value of 3.648. This is larger than 2.086, so I'm going to reject the null hypothesis. I want to make sure that I calculate D. Okay, D here in the bottom, I want the pooled standard deviation. Essentially what I do is I take the pooled variance and take the standard deviation of it. Yeah, there we go. No, not the standard deviation, square root. There we go. All right, so I work this magic and I get an effect size of 1.56. That is a massive effect. That is a very large effect. Okay, and we rejected the null hypothesis even with a small number of subjects. Let us look at the conclusion statement that we have here. So we reject the null hypothesis in favor of the alternative hypothesis that the population mean of questions answered correctly is different for subjects tested on reading passage, descriptive statistic, compared to subjects that just study the reading passage. Mean equals blah, 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 blah. I noticed that I haven't put the standard deviations here, so I'll need to make that change. Okay, make sure that you include those in your step 4s. T, with the degrees of freedom is 20, equals 3.648. And P, since we're rejecting the null hypothesis, is less than 0.05. And here we have Cohen's D. All right, I hope those couple of examples helped you out with doing independent samples t-test. And I hope you guys have a great day. All right, talk with you later, and good luck studying. Thank you. Bye-bye.